All right, so this is lesson 1-7. And in this lesson, we're going to actually officially write those theorems and prove those theorems. Remember a while back we talked about there's two different types of proofs. We can do the regular proofs like you did on your test and everything, where you're given and a proof, and it's something very specific about a diagram that you're given. Or, like we did in lesson 1-5, there's proofs that actually are written out proofs of theorems. Because remember, a postulate is something we accept as being true without proof. A theorem is actually a theorem because a proof can be written about it. Somebody proved it, and that's how it became a theorem. So in this class, sometimes when we learn a new theorem, we're actually going to write the proof of the theorem, officially prove it, so that then we can use it in proofs. All right. What was the one rule when you're writing the proof of a theorem? You can't what? Anybody remember? Yeah. Exactly. You can't use the theorem you're trying to prove as one of the reasons in that proof. And then, if you use it as a reason, you're assuming it's true, and we're trying to prove that it's true. So we're going to see a couple of proofs of these theorems, and then once we prove them, we can use them as reasons in proof. Okay? So officially, what is the definition of parallel lines? Ryan. Okay. Lines in the same plane that never intersect. Good. Now, I had to add the little phrase in the same plane because there are lines that never intersect that are in different planes. Those are called skew lines, which we'll learn another time. But they look like this. Almost like a highway and then an overpass highway going over it the other direction, right? If you looked at an aerial view, it would look like they intersected, but they actually don't. So we need to add in the same plane that never intersect. So, they kind of look like this. Okay, this little symbol means is parallel to. Transversal. What is the actual definition of a transversal? Yep. Good. A line that intersects two or more other lines, and they don't have to be parallel lines, actually. They become more meaningful when they're parallel lines because they create all these relationships, but they don't have to be parallel lines for it to be called a transversal. Transversal just goes through two or more other lines. All right, now, instead of writing definitions of these, same side interior angles, etc., I just figured we'd do a little sketch. Because picturing them and identifying them in a diagram is really what's important here. You don't have to write out, the description of what they are. You have to just recognize them. So alternate interior would be like that. Now, obviously, there's more than one pair in each of these sketches, but in order to not make it confusing, I just did one pair in each. Okay, an auxiliary line. This might be a new one to you. Auxiliary line. Have you heard the word auxiliary in English anywhere, ever? Auxiliary, what's it mean? You've heard it, but you're not sure what it means. Anybody ever use an aux cord? You know that stands for auxiliary chord? What's that aux chord do for you? It does, but it's basically an extension, right? It's something you have to add to your technology to make it do something else, right? You stick the aux cord in so that it plays the music from your phone or whatever, right? So an aux cord is a something you add in there to help you accomplish what you want to accomplish. So an auxiliary line in geometry is a line we add to a diagram to help us prove or solve something. So auxiliary line, basically you're adding a line to the existing diagram. Okay, the parallel postulate is kind of wordy, but it's a really basic concept. It basically says if you have a line, you can see this line L here, and a point not on the line, if I ask somebody to come up and draw another line so that it goes through that point and is parallel to the given line, they would draw something like this, right? Through the point, parallel to the given line. All right, now I ask somebody else to come up and draw another line that goes through that point and parallel to the blue line. Could they draw a different line? No. That's what this postulate says. This postulate says that there is only one line that is possible to draw through a point parallel to a given line. There is only one line possible drawn through a point and parallel to a given line. Of course, the phrase "a point not on the line" should be in there somewhere, but I think you get the idea, right? It's a point that's separate from the line. There's only one line that can pass through that point parallel to the given line. Okay, so we good? Okay, so now here's just a recap right here of the theorems that we've learned. They all say if the two lines are parallel, right? If a transversal intersects two parallel lines. So the hypothesis here for every single theorem is that the lines are parallel. If lines are parallel, then same side interior angles are supplementary. Alternate interior angles are congruent. Alternate exterior angles are congruent, and corresponding angles are congruent, right? So remember, the S's, same side, are supplementary. The rest are congruent. Only if the lines are parallel. Notice one little detail here. This one is a postulate, and these three are theorems. Again, the difference between a postulate and a theorem. Postulates we accept as true without proof. Theorems have been proven. So, can you think of why one of these is a postulate and the other three are theorems? Yep. Exactly. We can't prove these three without accepting this first one as true first. So one of them we use in the other theorems, proofs of the other theorems. So we have to accept one as true before we can prove any of them. However, when you write a proof and you're using these four things, I don't really care if you call them postulates or theorems. Like, I would just call them all theorems. Because it's sort of arbitrary which one is the postulate. In high school, when I took geometry, my book used corresponding angles as the postulate and used that to prove the other three theorems. So it's arbitrary which one, you know, in the big picture, they've all been proven. So we really can call them all theorems. But for our official proving purposes, we're going to use one as a postulate to prove the other theorems. Okay, so turn the page. These three are the three proofs of the theorems. And we're going to do the first one, maybe the first two together. So again, these are proofs of theorems. So very basic given and prove, right? Given these lines are parallel, prove that 4 and 6, so alternate interior angles, are congruent. So we're going to start with our given. And often, in a proof of a theorem, the given doesn't really lead to much because, you know, we haven't proven anything yet. But in this case, this is going to lead to our postulate that we're going to use. And our postulate is the same side interior angles theorem. So what statement could I make, since lines are parallel, what statement can I make from this diagram about same side interior angles? Yeah, Sylvie. Good. Angle 3 and angle 6, or angle 3 is supplementary to angle 6. And the reason is going to be same side interior angles postulate. Okay, looking in this diagram, what other relationship could we conclude about angles in this diagram? Yeah, Lorelai. Good. Angle 4 is supplementary to angle 3. Reason? Good. Linear pair postulate, right? 4 and 3 are a linear pair that makes them supplementary. So now we have 4 is supplementary to 3 and 3 is supplementary to 6. What conclusion could we make? Could we say 4 is congruent to 6 right now? Yes. No. We cannot use a transitive because it's not congruent, it's supplementary. This is where we can use the congruent supplements theorem to say angle 4 is congruent to angle 6. That's it. All right, you try that next proof. I'll give you a hint. It's very similar to the first one. All right, did you get that? Okay, any questions on that proof? Make sense, right? Two angles, both supplementary to the same angle. So 2 supplementary to 3 and 6 supplementary to 3. Okay, now for the proof of the alternate exterior angles theorem, we can use any of the theorems we just proved or the postulate, right? So we just proved the corresponding angles theorem and the alternate interior angles theorem. So now we're free to use those. and we can use them in this proof here. So we're going to start with A parallel to B. A parallel to B. And we're trying to prove alternate exterior angles. So we're trying to prove 1 and 7. So what could we do? Whenever you have proofs like this, you're really looking for the link. You're looking for how you can link your givens to your proof. So our given is basically the lines are parallel, so we have some relationships we can make. We're trying to get 1 and 7. So is there one angle that's related to 1 that's also related to 7? That would be what I would call the linking angle. Yeah, Connor. 5 links to 1. How? What kind of angles are they? Corresponding. And 5 links to 7. How? Vertical angles. So that's a good one because it has a relationship to both. So because of the lines being parallel, we could say angle 1 is congruent to angle 5 by the corresponding angles theorem, because we already proved that theorem. And then we can say angle 5 is congruent to angle 7 by the vertical angles theorem. Can I now say 1 is congruent to 7? What would be the reason? So this is all congruence, so we can use the transitive property of equality. Congruence. Does that make sense? Okay. I would like you to flip to the back page, because I just want to get this started with you. We're given a diagram. I call this the hashtag diagram, right? Because it's basically 2 sets of parallel lines. Both are marked parallel. Do you see that? There's like a double arrow here and only a single there. So we know L is parallel to M and P is parallel to Q. So in this exercise, you're deciding what relationships 2 angles have and writing it in. So first of all, the one angle they're giving us is that this angle here is 105 degrees. So what would angle 7 be? 105 also. Because why? How is it related? Good. So vertical angles theorem. Now, the next one says the measure of angle 6. What would the measure of angle 6 be? 105. Now, there's 2 ways you can get 6, right? You could maybe say it's alternate interior to the original one that they marked, but this is where you have to look to the end of the sentence that's on your paper and see what angle they want you to relate it to. So angle 6 is 105 because how does it relate to angle 7? They're corresponding, right? So we would put corresponding in here. And 6 and 7 have what transversal in common? Q, so that's what would go here. All right, so even though some of these angles you might think to get them a different way, you kind of have to look to the end of the sentence and see how they're related. So what about angle 8? Angle 8. And you might want to, label these as you go because sometimes it helps you. So 8 is also going to be 105, and they want us to relate that to 6. 8 and 6 are what kind of angles? Corresponding again, and what transversal? 8 and 6 both touch L, right? Okay, get the idea? All right, so our time is pretty much up here. Your homework for tonight is to finish the 1.6p worksheet that you started in class. You just did the circled ones. You're going to go back and do all of them, okay? And I would like you to finish this page. Not the proof, sorry. Finish up to here. You're not going to do the proofs yet because we didn't really finish. All right?